Hello, Daniel. It's Tuesday. Can you guys see all the trash behind me? I need to clean. So again, you didn't upload a video on Friday, meaning you get an additional punishment. You already have the punishment of taking 2 shots of barbecue sauce, and your new punishment is to pour a gallon of milk over your head. I don't care if it's skim, or 2%, or whole, hell, you can go out and milk a cow yourself, as long as a gallon of milk is dumped on your head. With that out of the way, I want to take this video to talk about a chemistry thing that I find pretty cool. But before I get to the coolness, I want to give some background information to clear up any confusion. Molecules can take on different structures but still have the same chemical formula. These are called isomers, and there are several different types of isomers, but the more notable are conformational and stereoisomers. Conformational isomers have the same formula and the same connectivity, but they don't have the same shape. For example, I have this ethane molecule here, and if you look along the central carbon-carbon bond, you can notice that the hydrogen atoms are staggered. But you can rotate this bond like so, and if you look along the central carbon-carbon bond, you can notice that the hydrogens are overlapping, therefore giving an isomer. Stereoisomers are based on the 3-dimensional arrangement of the atoms in a molecule. There are 2 types of stereoisomers. There's enantiomers and diastereoisomers. Enantiomers are non-superimposable mirror images of each other. For example, I have these 2 molecules here, and if you notice, they are mirror images of each other, but they are not superimposable. Diastereoisomers are non-superimposable, non-mirror images. Let's take a look at the enantiomers again, and if I switch the respective hydrogen and hydroxyl groups on one of the atoms, you can notice that they are no longer mirror images of each other, and they are no longer superimposable. They weren't superimposable to begin with, but that's the point. They are non-superimposable, non-mirror images. Now for the coolness I mentioned earlier. What I find interesting about isomers is that while they share the same chemical formula, they can have different effects, specifically those effects on the human body. Take cisplatin, for example. Cisplatin is used as an anti-cancer drug, but the isomer transplatin is toxic and deactivates said drug. Another similar example is the molecule thalidomide. Thalidomide was sold in the late 1950s as a wonder drug used to treat coughing, colds, and headaches. Thousands of pregnant women took this drug to relieve their symptoms, and scientists at the time believed that the drug couldn't penetrate the placental barrier. However, thousands of children were being born with serious birth defects that were linked back to this drug. This is because one isomer was beneficial and treated the symptoms they were supposed to, while the other was malignant and caused children to be born with these freakish birth defects. This is what I find really interesting, how molecules with the same chemical formula but slight differences in their structure can have such drastic effects. One of the things that's important, especially with pharmaceutical chemistry, is knowing how to separate the beneficial isomers from the non-beneficial isomers. So Daniel, I have a few things I want from you. First, I want you to tell me something cool you've learned during your freshman year of college. Second, I'm in the mood for a challenge, so I want you to give me one. People can leave suggestions down in the comments, and I'm holding the ethane molecule. Third, I want you to do your punishments. Remember, 2 shots of barbecue sauce and pouring a gallon of milk on your head. I'll see you on Friday.